Hi everyone. Now for this lesson, I'm going to show you how you're going to apply what you learned in the earlier video to solve physics problem related to forces and acceleration. For this video, I'm going to focus on the application of Newton's second law on the cases where your mass is constant. In the subsequent videos, I'll cover situations where the Newton's second law is being applied in situations where the mass is not constant. Because Newton's second law is a big theory, is a big law that applies to different situations differently, and I'm going to focus on situations where the mass is constant. Two bodies A and B, so you're supposed to find, say for example, the question asked you for the acceleration of the system, and given that the situation is that you've got A tied to a string and then tied over to B, and B rests on a rough surface. So how do you approach this question? First thing, identify the forces acting on each body separately in a free body diagram. Let's start off with body A first. And let's assume that the acceleration is this way. Naturally, it has to accelerate this way because they're tied by a string. And the string cannot, it cannot go the other way, it will break, right? B cannot go the other way. So let's say if A would accelerate downwards, we'll keep that worry if that you may ask yourself, what if the actual acceleration is the other way? We'll talk about it later. So if the body A is accelerating downwards, now we have the tangent, remembering the length of the arrow, weight must be, and for good practice sake, I'll put WA because you've got two bodies, then you'll be confused about W. So what we have over here is WA and tangent, and WA is longer than T because acceleration is downwards. Any other forces? Friction, air resistance, we assume that it doesn't exist in this very idealized world, so that's all. For this body over here, B, you've got your weight of B, you've got a tension that's always pull. Remember, we learned in the earlier video that tension always pull. You've got frictional force acting on the surface and downwards, and you've got the normal contact force. That's all for body B. So now how do we apply the equation for the body A and body B so that we can find the necessary? Now remember that when you apply Newton's second law, this is something that I'd like you to remember. But we erase this away so that it creates space for the equation. One of the things that I would like you to remember is that you always take the direction of acceleration as the positive direction. It doesn't matter if you take the other direction as the positive direction, but for convenience sake, if you take the direction of acceleration to be positive, this will always be positive ma. Otherwise, it will be not as neat if you have the negative ma over here. So for body A, downwards is acceleration. So mag minus tangent is equals to ma. That's your equation 1. For body B, what you have over here is summation of F equals to MBA. So just need to be careful over here because we are talking about acceleration, which is in this direction. We are only concerned with the forces that act in that direction. So WB doesn't act in that direction. It is a component of WB that acts in that direction. So if we assume that this angle over here is theta, then the forces that acts this way, or the force that acts this way is the only force that acts this way is a positive force, minus the forces that acts this way, which include MBG sine theta and F. So now you've got equation 2. So in a question that involves this kind of situation, you'll always be given everything except for two variables, and you'll be able to solve it using these two variables, these two equations for the two unknowns. But I'd like to recap what we went through just now. It is important for you to distill what is the most important thing. First, identify the forces, draw the free body diagram, same thing. Next, apply Newton's second law where it is in the form for the case where the mass is constant, and taking the direction of acceleration to be positive. Anything that points in the direction of acceleration is positive, opposite negative. In the direction of acceleration positive, in the opposite direction negative. And you'll always be given two equations, two unknowns. Or if you have to do three equations, three unknowns, then so be it. But no matter how many bodies you have to handle, it will always be the case. Let's try it for this situation, where you have something that moves in a vertical direction. Classic case, very classic. Where you have a man pulling on a string that pulls on the lift itself. So let's identify the forces acting on the man and the lift. So let's take a look at the man. You've got the weight of the man, you've got the normal contact force by the lift on the man, and you've got this is the part where it's interesting. The tension is up or down. Remember tension? The difficulty over here, some of you may say that it's up, but the difficult part is that when the person pulls down. So remember, the tension always pulls on the body that it is attached to. So if it pulls, there's only one direction you can go. If you look at it from the Newton's third law perspective, the person pulls down on the rope pulls on the person upwards. Alright, so these are the three forces. Anything else? Checklist. Up thrust, no. Air resistance, no. Velocity, frictional force, no. So these are the forces acting on the person. Alright, next one. The weight of the lift, the tension, of course. This tension and this tension are the same, by the way. Do note. And I'll explain, if I have time later on, I'll explain why the two tensions on two bodies must be the same. So let's take a look at this situation over here. Any other forces? How about the interaction between the man and the lift? Is it the weight of the man? Remember just now, in the earlier video, we mentioned that the weight of the man is the interaction between the earth and the man, nothing to do with the lift. The force, the interaction between the man and the lift is the normal contact force. So normal contact force by the lift on the man, normal contact force by the man on the lift. And these are the three forces acting on the two bodies. Let's assume that the acceleration is upwards, then the equation for this, remember, direction acceleration is always positive, 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 negative. T plus n minus n mg, mass of man g, equals to mass of man A. Same thing, if this lift also accelerates upwards, positive, negative, negative, weight of lift minus n. Notice how I religiously add the subscripts in. Mass of man, weight of lift, mass of lift. Very important, otherwise you will meet with difficulties substituting. You may make careless mistakes if you don't do the subscript properly. Sometimes in exam conditions you might be tensed up and you might make wrong substitution. So it's always good practice for you to do this kind of little tricks, have this kind of little tricks inside your equation, inside your problem solving techniques, so that it helps to reduce the number of the careless mistakes that you have. Alright, so I hope that this very short lesson shows you how you can apply the Newton's second law for fixed mass situation, and using what we learned in the previous video on free body diagram to help you solve questions on multiple body problems. Alright, I remember now. Just now I mentioned that I'm going to show you if I have time, and I do have a little bit of time left in the video, for me to show you why is it that when you have two bodies or multiple bodies with a tension in between, the tension on these two bodies must be the same. Let's call this body A, body B. Let's call this tension 1 and tension 2, assuming that it's different. So this is tension acting on A, this is tension acting on B. Now let's consider the rope over here. Let's consider the rope as a body. Alright? So therefore, on the rope itself, the tension 1 will be pulling on the rope, tension 2 will be pulling on the rope this way. So if the acceleration is this way, then you got T1 minus T2 equals the mass of rope A. Now the acceleration of the rope obviously is not 0, but the mass of the rope, if it is 0, if mass of rope is equals to 0, no matter what's the acceleration, tension 1 will be equals to tension 2. So therefore, when you hear that the teacher say that tension 1 is equals to tension 2, tension is along the same rope is the same, you need to remember that there's this important assumption that the mass of the rope is 0. That is to say, if the mass of the rope is not 0, it will not be the same. Okay, so you have to be aware of this, because in exams you may be asked, what's the situation, or what will be the case? What will happen to the tension if the mass of the rope is not negligible? Then it leads on to another question. So which one is bigger, T1 or T2? I think it's not difficult for us to see that if mass of rope is not 0, T1 will naturally have to be bigger than T2. So the tension will decrease along the rope. Okay? So I hope it gives some insights into why tension along the rope has to be the same, because the situation that you handle, most of the time, in fact all the time, the rope is massless, or the pulley is frictionless. Okay, cool. I hope that this is helpful for you. and that helps you in solving problems in the future. Thank you.